Introduction to Differential Equations. Let's start with some terminology. A differential equation is a mathematical equation that relates a function or functions with its derivatives. A solution to a differential equation is any function y which satisfies the given differential equation. Initial conditions are values of the solution and/or its derivatives at specific points. They are of the form y of a equals b, or the nth derivative of y at a equals b. Only one solution will meet the given initial condition or conditions. Differential equations with initial conditions are sometimes called initial value problems. Differential equations are covered extensively later in calculus, but for now, we will solve some basic ones. In this first example, we want to solve the differential equation y prime equals sine of the quantity pi times x given y of 1/2 equals 2. So let's go back and take a look at this differential equation for a moment. So we said a differential equation is an equation that relates a function or functions with its derivative. So here, this is an equation. It has an equal sign. And the way I like to think about it is that it's an equation that involves a derivative. So y prime is involved, just a first derivative. And what we're solving for is y. We're solving for the original function. So in algebraic equations, something like x plus 2 is equal to 4, we're solving for the missing value of x, the variable. In a differential equation, what we're solving for is that original function y. So here, to go from y prime, the first derivative, to y, I need to take an antiderivative or find an indefinite integral. So here, y is equal to the integral of sine of pi x dx. And so when I find the general antiderivative of this, the antiderivative of sine of pi x, I'm going to get a 1 over pi, 1 over the slope here, since this inside is linear. So 1 over pi is going to come out in front. And the antiderivative of sine is negative cosine. So I'm going to have that negative in the front, cosine of pi x. And then our general antiderivative has the generic constant plus c. So I have y equals negative 1 over pi cosine of pi x plus c. This is the most general solution to this differential equation. But we're also given this other piece of information called an initial condition. So it's a point. This is an x value and 2 is a y value. And what this point allows us to do is it allows us to find a specific function without a generic constant in it. So we're able to solve for this value of c. So I'm going to go ahead and do this work off to the side. I'm going to substitute in 1/2 into x and 2 into y in order to solve for the value of c. So 2 is the output, 2 is y. So 2 is equal to negative 1 over pi cosine of pi times 1/2. So that's pi over 2 plus c. So now c can be solved for. I can evaluate cosine of pi over 2. So the x value at pi over 2 is 0. So this is 2 is equal to negative 1 over pi times 0. That's 0 plus c. So c is equal to 2. Now the answer is not 2 to this differential equation. The answer is substituting the 2 back into the equation for y to find a particular solution that satisfies the initial condition. So negative 1 over pi cosine of pi x plus 2. This is my solution to this differential equation with an initial condition, also called an initial value problem. In this next example, I want to solve y double prime equals 2x given y of 0 equals 1 and y of 1 equals 1. So I do have a differential equation. I have an equation that basically involves a derivative, this time a second derivative. But I'm always in search of y, the original function. So to get from y double prime to y, I'm going to have to take the general antiderivative twice. So let's go ahead and start by saying that if I integrate just once, I'm going to get y prime. So y prime is the integral of 2x dx. Well, the integral of 2x is x squared plus some generic constant c. So far I have y prime is equal to x squared plus c. So this is a general solution that finds the first derivative. And I do have two initial conditions, but neither of them involve y prime, so I can't actually use either of these. You may have an initial condition that involves a derivative, but in this case we don't. So we are still in search of that original function y, so I'm going to have to integrate one more time. So now I'm going to say y is equal to the integral of x squared plus c dx, remembering that c is some numerical value. So when I integrate this, I'm going to get x cubed over 3 by the power rule for integrals plus c times x. So remember, we're integrating a constant, so that means that we're going to have to put the variable x behind it because, again, think about it in the opposite direction, the derivative of c times x, which is bc. And then I'm going to need another generic constant, something other than c. So I'm going to say cx plus d. We could use c1 and c2. It doesn't matter, but it does have to be a different variable. So now, this is what I have for y, x cubed over 3 plus cx plus d. Notice that there are two missing variables, c and d, and I have two initial conditions. So I'll be able to solve for c and d to get my answer. So let's start by using the initial condition y of 0 is equal to 1. So that means when I plug 0 into each x, 1 has to come out for y. So that's what I'm going to start with. So 1 would come out when I plug in 0. 0 cubed over 3 plus c times 0 plus d. So I have 1 is equal to d. d is equal to 1 right there, right? Because both of these zero out. So I found one of my values, and I'll go ahead and use the other initial condition. Y of 1 is equal to 1. So when I plug in 1 into each x, 1 has to come out. So 1 is equal to 1 cubed over 3 plus c times 1 plus d. But we already have a value for d, so let's go ahead and substitute that in so that in this equation we're only missing c. So here's what I have. I have 1 equals 1/3 plus c plus 1. If I subtract 1 from each side, right, I get 0 is equal to 1/3 plus c. Subtract the 1/3 to the other side. C is equal to negative 1/3. All right, so we found the value of c and the value of d. The answer is substituting those into the equation for y. So y is equal to x cubed over 3 minus 1/3 x plus 1. Now in this example, we have a little bit of context. We're told that a particle is moving with the given data. Find the position of the particle. So here's what we're given. We're given acceleration. Acceleration is 6t plus 4. And then we're told that the velocity at 0 is equal to negative 6, and the position s at 0 is equal to 9. So we are given acceleration, one piece of information about velocity, the initial velocity, and one piece about position, the initial position. Now, this is a differential equation because this does involve a derivative. Acceleration is a second derivative of position. and we're being asked to find the position function, so that original starting function. So we're going to have to find two antiderivatives here, and we have two initial conditions. So if I start with acceleration, if I find the general antiderivative once, that's going to get me the velocity function. So I'm going to say v of t is equal to the integral of 6t plus 4 dt. All right, so if I find the antiderivative, that's going to be 6t squared over 2 plus 4t plus c, which is 3t squared plus 4t plus c. This is my general velocity function. It's an entire family of functions because of the generic constant plus c, but I have an initial condition involving velocity. I know that when I substitute in 0 into t, what's going to come out is -6. So this initial condition will allow me to solve for c. So I'm going to stop here and solve for c. So that means that when I plug in 0, I'm going to get out -6. So -6 is equal to 3 times 0 squared plus 4 times 0 plus c. Well, it's kind of nice. I just get c is equal to -6. So that means that I have my v of t function is 3t squared plus 4t minus 6. Well, I'm not done yet. I want to find the position of the particle, which means I want the position function. This isn't asking me for a specific numerical value. Finding the position of the particle means find the position function. So I'm going to integrate again, or find the general antiderivative again. So s of t is the integral of this velocity function, 3t squared plus 4t minus 6 dt. So here we'll have 3t cubed over 3, add a power, divide by the new power, plus 4t squared over 2 minus 6t plus, I'm going to use a different variable. Even though I've already solved for c over here, I don't want to use the same variable in the same problem, so I'm going to say d over here. So here is my position function, but it is not a specific one yet because we want to solve for d. Let's clean it up a little bit first. The 3's cancel. We have t cubed plus 2t squared minus 6t plus d. And I know that when I plug in 0 into position, 9 comes out. So a 9 comes out when 0 is substituted in to each t. And it's kind of nice again, right? All of these t terms 0 out, and I end up with just d is equal to 9. All right, but that's not the answer, right? The answer is the actual function. So I'm going to go ahead and move all of this over to make space and say that the final answer is the position function here. And that's going to be s of t is equal to t cubed plus 2t squared minus 6t plus 9. So this is the position of the particle, of course, at any time t. So this question challenges us to remember the relationship that starting with position, the derivative is velocity, and then the derivative of velocity is acceleration. So if I work backwards, this process of finding the antiderivative, if you start with acceleration, the antiderivative is velocity, and then if I take the antiderivative of velocity, I get myself to position. To formalize what I just said with some notation, if we start with position, we take the derivative, we get velocity. We take the second derivative of position, or the first derivative of velocity, we get acceleration. If we start with acceleration, and we integrate acceleration, we get velocity. If we integrate velocity, then we get position.